Thanks, everybody. Let's talk a little bit about curvature. Now, when we parameterize our curve with respect to arc length, remember that we had the unit tangent vector as just being dr ds, where s is going to be our arc length parameter. Now, if we parameterize with respect to any other variable, we can also get the unit tangent vector by just taking the ordinary derivative and then normalizing it by the length. That's also going to give us the unit tangent vector. And so this nice property, because we take the dot product and it's always 1, if we take the derivative with respect to arc length of both sides, what we end up with is something that looks like the product rule over on the left, and on the right side, because we're taking the derivative of a constant, we just get 0. Now what that means is that the derivative of the unit tangent vector dotted with the unit tangent vector gives us 0, so that the tangent vector and the unit tangent vector and its derivative are really going to be orthogonal vectors. So we can ask ourselves the question is, what does this vector dt ds actually mean geometrically? Well, for a little bit of intuition, we've got t being our unit tangent vector. That's already a first derivative. And so the second derivative, dt ds, should relate to our concavity if we're kind of thinking intuitively from Calc 1. If we kind of think about it from the physics perspective, then the second derivative is going to give us something that looks like accelerations. It's going to give us forces. It's going to make things kind of move or curve or bend, is really kind of what we're thinking in that case. So if we take the special case of a circle, and then we start looking at dt ds, well, if we just look at our circle, gamma of t being r cosine of t, r sine of t, we've got a circle with a radius of r. We compute our ds, our arc length form, and it ends up just being r dt. When we plug this into our arc length function, the integral of 0 up to t for r d tau, that's just going to give us s being r times t. Well, solving for t gives us t is equal to s over r. Plugging this back into our parameterization just gives us gamma of s being r cosine of s over r and r sine of s over r. And our interval that we have for s goes everywhere from 0 up to 2 pi r, which we would recognize that as being the circumference of our circle. That was just a little bit of a review of parameterizing a curve with respect to arc length. So now if we take the unit tangent vector, so we take the derivative of that, we end up with minus sine of s over r and cosine of s over r. So that gives us the unit tangent vector. Now taking the derivative of that, which this is the guy that we're really after, we end up with a minus 1 over r times a cosine of s over r and a sine of s over r. Now if we're going to relate this back to our original parameterization, this looks like a minus 1 over r squared times our original vector gamma of s. So this is telling us that in the particular case that we're dealing with the circle, that we get a vector that's going to be parallel to our original position vector. And so that's going to be of importance. If we kind of look at the picture of that, what we've got is we've got our unit, as we're tracing out the circle, we've got our unit tangent vector that's heading off in this direction, and then the derivative of that vector is going to be the vector kind of pointing back towards the origin. So remember, kind of if you're thinking about centrifugal force, then, or thinking about back to the physics standpoint, that what's going to make you curve in a particular direction is going to be a force kind of pointing you back towards the origin. So this kind of also makes sense from our physics perspective. Well, if we look at the length of the derivative of the unit tangent vector, we end up with just something that's just going to be a constant 1 over r. So now we end up with something that really looks like the reciprocal of our radius. So to kind of see what happens now geometrically along with this, let's go over to GeoGebra and view an example. So now maybe to gain some intuition as to what's happening with this unit tangent, or the derivative of this unit tangent vector, let's do an example where we're taking a particular point. So let's say that we're taking this point here at A, and let's construct a circle. So let's do a radius for our circle. Let's say R for the radius, and we want this thing to go from, say, 0 up to, let's make it 1500, and we'll do steps of 1 for that. And for our animation, let's just say that we don't want it to go, just want to increase it 1 time. All right, so now what we want to do with this R is let's construct a line segment of a given length, and we want it to be from our point A that we chose, and let's make it length R. Okay, so we don't need that necessarily. And so now what I do want to do is let's do a circle, and we want the circle centered at this new point B, but we want it to pass through this point at A. Now, of course, since our radius is just 1, everything looks like a circle. It looks like it's bending nicely, and it actually looks like a circle. But now what happens as we start to allow our radius to increase? So let's look at now geometrically what happens just from our point of view when we're kind of zeroing in on everything that's on the screen. So we turn on the animation, and what happens? And wow, okay, this is interesting. If our radius becomes big enough, the viewpoint that we have is that it really just looks like we're standing on a vertical line. We really can't tell the difference geometrically. That once the radius gets so big, we're zoomed in so close, that's really all that we can see. Now, if we do zoom out a little bit, if we zoom out from this thing, and then if we zoom out far enough, what we are seeing is that our line does actually bend, but we've got to zoom out far enough to really be able to see that bending happening very much. So now, I mean, we've zoomed out, our scale is out to 300, but if we were in closely enough, what we're really seeing is something that looks virtually like a straight line. Now, this is going to be important kind of coming up in the next video when we really start getting into a little bit of meaning as to what this derivative actually is going to be related to. And so the length of this length of the derivative of this unit tangent vector is really going to be something that we're going to call curvature. So stay tuned for that, and we'll be back in just a little bit.